Hey guys, welcome to the 9th episode of Short Bits by Shorty. This is also the first video posted on YouTube. We're also on YouTube now. Feel free to search Short Bits by Shorty on YouTube in quotation marks, or else you'll get some weird random rap videos. So search Short Bits by Shorty inside quotation marks, and you'll get the channel. Everything's organized by class. We have ID, nephrology, and now we have psychiatry folder or playlist. So check out the videos in there now. Before I start, just one disclaimer. Be sure to know all the concepts and the structures I present in here, which are also the structures and concepts Glenn presents. All I'm doing is clarifying those concepts. I'm not presenting all the examples, because examples are just examples. Don't know them because they're just there to illustrate the concepts. And I will indicate examples with clouds, which may or may not be yellow. So know everything outside the clouds. Clouds are just there to illustrate examples. So if I give you any structure that's not inside the cloud, be sure to know them, because I'm also including structures that are not in the handout but are in the slides. Because he does mention some important structures in the slides that aren't necessarily in the handout. So know all the concepts, know the structures. If you know the concepts, you can answer any question he throws at you that may or may not have been in the handout. He just wants to see if you can apply the concepts to structures or whatever he throws at you. Okay, to begin, here we go. Okay, so this is just a screenshot from the handout. I'm not going to explain this since it's pretty self-explanatory. You guys have read words before. If you have any questions on it, let me know. Otherwise, it's in the handout and it should be self-explanatory. I'm just screenshotting it there because he said it's important according to the slides. Okay, so to name benzodiazepines, you're going to find the bicyclic ring structure or the part of the molecule with the two rings. So here are your two rings, ring 1, ring 2. Now you're going to, number 1, divide it into the component rings. So here's ring 1, ring number 2, ring 1, ring number 2. Now you're going to number it. Step 2, number it. So always use the lowest numbering when you're doing the numbering. So you're going to start with, I should write start with the nitrogen. So numbers start with nitrogen. Pick a nitrogen, any nitrogen, as long as you get the lowest numbering. So let's say we start with this nitrogen. So we're gonna go, I don't know, 1, 2, 3, 4. And if you start with this nitrogen, you get the same thing. 1, 2, atom number 3, atom number 4. What if you go the other way? You're gonna get 1. Oh. 1, 2, atom number 3, 4, 5. You get 1, 5. Going the other way, you get the same thing. 1, 2, 3, 4, 5. So we see that the numbering is 1, 4. 1, 4. Benzodiazepine. Ooh, hoping you read that. That just says diazepine. Now how do you get the letter inside the bracket? So now you're gonna follow the numbering convention. So you're not gonna go this way when you give the letter. You're gonna go either this way or this way, because it follows the numbering pattern that gives you the lowest number. So what if we go this? Now we're gonna start with this nitrogen and letter things this way. You're also gonna start with nitrogen side. So start with the side with the nitrogen. So let's try A, B, C, D, E, F. So now I stopped at F because F, this side corresponds to the side where it joins with this side. So go until you find the side where it joins with the side of the other ring. So this right here corresponds to this side joining, and that's F. So what if you start with this nitrogen and going this way? Because it also gives you the numbering of 1, 4. So now we're going to try, I don't know, what color do you want? Red. We're going to try A, B, C, D, E, E. So E is lower than F, and it also follows the numbering convention. It also follows how you number the rings. So now we're going to label it with E. So now it's 1,4-benzo-E-diazepine. So let's do another one as an example. Okay, so I did step 1 for you. Found the ring structure and divided it into its components. So here's ring 1, here's ring 2. Now we're going to number it starting with a nitrogen. So let's see. You want to get the lowest number as always. So start with this nitrogen. And let's say we go this way. So let's go 2, 3, 4, 5. Starting with the other nitrogen, this one, you get the same thing. 1, 2, 3, 4, 5. So let's start this nitrogen going the other way. 1, 2, 3, 4. That gives you 4. 1, 4. Start with this nitrogen going the other way. You get 1, 2, 3. Atom number 4. 1, 4. Same thing. So now we're going to name it 1, 4. Benzo blank diazepine. That says diazepine. I don't care. So how'd you get the lettering? So remember, you start with you follow the numbering convention that gave you the lowest number. So you can either go this way or this way, because it also gave you 1, 4. So let's try this way. A, B, C. So B is the side where the two rings joined. This side corresponds to this. So that's B. What if you try the other side? Other way. So let's try, some one more color. This is A, B, C. So that also gives you B. So now B is the answer. So this one is a 1,4-benzo-B-diazepine. Okay, so first we're going to talk about the simple benzodiazepines, and our prototype for these is diazepam. So to explain the naming convention, here's chloro at the 7 chloro, 7 chloride at the 7 position, 1 methyl at the 1 position, 5 phenyl ring at the 5 position, 3 third position hydrogen, third position, anything that's not explicitly attached to a carbon is a hydrogen, so 3 hydrogens. Okay, so here's the important part. 1,4-benzoidiazepine. So it goes, if you just split into its components, you can go 1, 2, 3, 4, 5. That gives you 5. Or you can go 1, 2, 3, 4. That's 1, 4. Now you're going to follow the numbering convention. So you have to go this way or this way, since it also gives you 1, 4. 1, 2, 3, 4. So you can go A, B, C, D, E, F. You do that. Or A, B, C, D, E. So that gives you your E. Remember, always follow your numbering pattern when you get the lettering. Let's see. And this is 1,4-benzoidiazepine. And ON corresponds to your ketone at the 2 position. Ketone at the 2 position. Okay, so here's the metabolism of chlordiazepoxide and diazepam in both word form for people who like things in words and in chemical structure form, so you guys understand the concept behind things. Okay, so let's start with that chlordiazepam. Oh, by the way, the yellow are the minor pathways, and everything in blue is a major pathway. Everything in red is, I'm just highlighting things. So red is just highlighting things or numbering things. Yellow is minor pathway. Blue is major pathway. Okay, let's start with chlordiazepoxide. So chlordiazepoxide, first step is you're going to demethylate. Second step, you're going to convert the carbon to oxygen, convert it to a carbon-oxygen double bond. This gives you diazepam, which is lorazepam N oxide. Because it's called lorazepam N oxide, because when you lose the N oxide and convert it to just N, you get just lorazepam. So lorazepam is just lorazepam N oxide without the N oxide. So lorazepam N oxide or diazepam is a precursor to lorazepam. Major pathway, it's going to convert to oxazepam by hydroxylation or addition of a 3-position hydroxyl. And oxazepam is going to be glucuronidated and excreted. So major pathway from chlordiazepoxide to excretion is chlordiazepoxide to diazepam to lorazepam to oxazepam and glucuronidation. This goes by step 1, demethylation, step 2, conversion to carbon to oxygen double bond, step 3, loss of the N oxide to just nitrogen, and step 4, hydroxylation. Now let's look at diazepam. So diazepam is also gonna go into the first step of demethylation but instead of going to diazepam, it goes straight to lorazepam. Diazepam straight to lorazepam. And then it goes to this same major pathway, hydroxylation, or addition of 3' hydroxyl to oxazepam. Oxazepam is going to be glucuronidated, then excreted. So diazepam is goes from diazepam to lorazepam to oxazepam to glucuronidation and excretion by demethylation and hydroxylation. So remember, chlordiazepoxide has 4 steps: demethylation, conversion to carbon-oxygen double bond, loss of N oxide, and hydroxylation. Diazepam has 2 steps: demethylation and hydroxylation. Now let's look at the minor pathways. So let's start with chlordiazepoxide again. So chlordiazepoxide is demethylated and then converted to carbon-oxygen double bond to diazepam, or also called lorazepam N oxide. Now the minor pathway is you're going to add a hydroxyl at a 9 position or hydroxyl at the 4' position. That gives you an aromatic, some other ring, and then it's glucuronidated and excreted. In terms of diazepam, the minor pathway includes demethylation to lorazepam. That's the major pathway. Now the minor pathway is going to be same thing as the chlordiazepoxide minor pathway. Add a 9' hydroxyl or 9 hydroxyl or 4' hydroxyl to give you some aromatic ring, some ring system, and you're going to glucuronidate it and excrete it. So to get temazepam from diazepam, which is another minor pathway, instead of demethylating and going to the 9 hydroxyl or 4' hydroxyl, you're just going to go straight to the hydroxylation, but at the 3 position, to give temazepam. And as a first, just like the others, chlordiazepoxide into diazepam, first step is demethylation. So demethylation, just like diazepam and chlordiazepoxide, which gives you oxazepam. Oxazepam goes straight to glucuronidation and excretion. Easy way to memorize the minor pathways. See, 9 plus 4 is 13. 13's bad luck, which I hope you don't have during this exam. Bad luck. You don't want bad luck, so you go through the minor pathway. So 9 plus 4 is 9 plus 4 is 13. which is bad luck, and you want to avoid them. And minor pathways aren't as good as major pathways, so bad luck's not as good as good luck. And so 9 and 4 hydroxylation are the minor pathways. And this has a 3 and 3 hydroxyl, and this also has a 3 hydroxyl. Easy way to remember that. That's how I remember it, at least. So now let's look at this in picture form. Chemical form. So let's start with chlordiazepoxide. So chlordiazepoxide, remember, first step is demethylation. So it's going to lose this methyl group up here, and to get this structure, which has no methyl group. Next step is conversion to C double bond O, which you see over here. So first step is demethylation. Second step is conversion to C double bond O. Now, to go from diazepam or diazepam N oxide to diazepam, you're going to lose the N oxide. So the N oxide is right here. You're going to lose that to form just an N over here by adding some hydrogens. Major pathway, you're going to add a 3' hydroxyl over here to get so this is a 3' position. You're going to add it over here to hydroxyl to get oxazepam. Oxazepam is going to be glucuronidated and excreted. Chlordiazepoxide minor pathway. Remember, first step is demethylation. Next step is conversion to C double bond O. C double bond O. Now your minor pathway. Remember, 9 plus 4 is 13. 13 is bad luck. So 9 hydroxyl. This is your 9 position. I label it here for you. 9 positions right here. Over here. 9 position is over here. Add a 9 hydroxyl, or you can add a 4' hydroxyl. Over here again, over here. So 4' is over here. You're gonna add a hydroxyl at the 4'. So you can either do 9' position hydroxylation, or 4' hydroxylation at the bottom. So top or bottom. Top or bottom. Then from here, you can glucuronidate it and excrete it. That's it. So now let's look at diazepam, which is over here. Remember, first step is demethylation. Demethylate the N. Demethylate the methyl attached to the N to get no methyl attached to the N. You get diazepam. Major pathway, you're at 3' 3 position hydroxylated. So here's a 3 position. Add hydroxyl over here. Glucuronidate it and excrete it. Minor pathway. Diazepam. First step is demethylation. Remember that. If you don't learn anything from this video, first step is demethylation. When in doubt, demethylate it out. First step is demethylation. So remove the methyl attached to the nitrogen. You get diazepam. Then you get 9 hydroxylation or 4' hydroxylation. Remember, 9 plus 4 is 13, which is bad luck. So remember, 9 position hydroxylation over at the top, or you can do 4' hydroxylation at the bottom. Glucuronidate it, then excrete it. Minor pathway number 2, diazepam to temazepam. Here the first step is not demethylation, but you can reverse the steps. So you can do... Oh yeah, it's already searched for you. Okay. Never mind. Ignore what I just said. Okay, so diazepam to temazepam. It goes 3' hydroxylation first over here to get the temazepam. Then you demethylate it to remove the methyl group to get oxazepam. Which makes sense because temazepam has hydroxyl but still a methyl, but you want to remove the methyl to get oxazepam because oxazepam has no methyl. So diazepam to temazepam, hydroxylate it, then you can demethylate it. Then glucuronidate it and excrete it. Once again, diazepam to temazepam to oxazepam, you hydroxylate it, then you demethylate it. Not demethylate, then hydroxylate. So hydroxylate, demethylate from diazepam to temazepam to oxazepam. And cool thing he mentioned, in this diazepam pathway, you can hydroxylate first. Oh, man. And then you can demethylate for the major pathway. So as to show you here, from diazepam to lorazepam, you demethylated, then hydroxylated. But in the major pathway, this blue pathway, you can hydroxylate, then demethylate. But, just when in doubt, demethylate it out. Just a tidbit in case he does test you on it. The diazepam pathway, you can start with hydroxylation, then demethylation. But remember that to diazepam to temazepam, it's always hydroxylation, then demethylation. If you want to go from diazepam to temazepam. Remember, only diazepam to temazepam, you have to do hydroxylation, then demethylation. But for the major pathway from diazepam to oxazepam through lorazepam, you can hydroxylate, then demethylate. But when in doubt, just demethylate it out first. Okay, so just to go over some basic definitions, you can see my test you on them. SAR versus SAR versus Sapphire. So SAR gives you structure-activity relationships. Sapphire describes structure-affinity relationships. So SAR measures activity. Sapphire measures affinity. And remember, affinity is how well a molecule binds to a receptor. Efficacy refers to how well a molecule activates a receptor or produces an effect on that receptor. So now we're going to talk about the Sapphire of simple benzodiazepines using diazepam as a prototype. Just the concept, just to remind you, remember that higher Ki values lead to less binding. So Ki of 10 binds better than a Ki of, 4,000. So now let's begin. Okay, so now let's look at first position 1. So, and nitrogen is optimal. This is position 1, by the way. Position 1. Nitrogen is optimal, but it's not required. You can replace it with an sp2 hybridized carbon. So, for example, so if you have this N, you can replace it with carbon nitrogen or a carbon sulfur double bond, or you can replace it with a carbon double bond. So an sp2 hybridized carbon refers to a C double bond N, C double bond S, or a C double bond C. So now let's go back to you can still get activity if you replace the nitrogen with a C double bond, an sp2 hybridized C, or a C double bond S, C double bond N, C double bond C. So now let's go back to our original diazepam. So this has a Ki of 10. So what if you replace this CH3 group with something else? So let's say you replace it with a hydrogen. That gives you diazepam, and diazepam has a Ki of 10. So now you went from originally. Oh, diazepam, which has a methyl group. Now you're going to change it to a hydrogen, which is smaller than a methyl group. If you don't believe me, let me draw it out for you. CH. See how big that methyl group is compared to just one hydrogen? So that's diazepam. Now let's change it back to diazepam. So remember, diazepam is just one hydrogen. And that still has a Ki. That still has a Ki of 10. So that means they bind at the same strength to each other. So now what if you increase the size of this? So let's say you make it two. Ooh, wrong color. Let's make it 2 carbons. So carbon. Oh, nope, just kidding. Carbon, hydrogen. See how much bigger it is? So now, if you increase the size of the group attached to the nitrogen, affinity decreases. So, 3 principles for the first position. Number 1, nitrogen is optimal but not required, because you can replace it with principle number 2. You can replace it with sp2 hybridized carbon, which means a carbon double bond nitrogen, carbon double bond sulfur, carbon double bond carbon. And principle number 3, bigger groups attached to the N means a lower affinity, which means higher Ki. So you want the smallest group as possible attached to the N, or you can replace it with an sp2 hybridized carbon, which includes carbon double bond nitrogen, carbon double bond sulfur, carbon double bond carbon. So, small groups, which includes hydrogen and sp2 hybridized carbon. Okay, position 2, which refers to over here. That's position 2. You can have, what's optimal is a carbon double bonded to something, or an sp2 hybridized carbon. And remember, sp2 hybridized carbons, as I said before, are over here. Carbon double bond nitrogen, carbon double bond sulfur, carbon double bond carbon. So, yeah. So what's optimal is anything with an sp2 hybridized carbon at the 2 position. Optimal. Oh, by the way, just like I said before, this should be in a cloud, because don't memorize it. I'm just illustrating concepts with examples. It's cloud. This should also be in a cloud. Well, that's diazepam, but whatever. Okay, now let's do midazolam, which will illustrate some other concept. So here's position 2 again. This is diazepam. There's a bubble. Don't memorize it. So why is this active? So why is this active even though it has no carbon double bonded or sp2 hybridized carbon? So why is it still active? Well, remember it is metabolized to diazepam. And how was this? Well, if you compare these two structures, this is metazepam, this is diazepam. So all you gotta do, these are pretty much similar except diazepam has a C double bond O. So all you gotta do in metabolism is just add a C double bond O, and you can still make it active. So why is metazepam still active as an anxiolytic? It's because it's metabolized to diazepam. All you gotta do is just add a C double bond O. So remember, position 2, you just need an sp2 hybridized carbon. But even though metazepam doesn't have it, it's still active because it is metabolized to diazepam by just adding that C double bond O group. Okay, so now we're going to look at position 3, which is 1, 2, 3. Right here. Okay, so hydrogen is optimal. Like I said over here, hydrogen is optimal, but larger groups produce less affinity, which means higher Ki. So remember that any atom that is not written out is basically attached to a carbon is basically a hydrogen. So over here you have hydrogen. So hydrogen is optimal. But what if you start adding other groups? For example, remember the Ki, well, you don't have to remember, but I'm just writing it for you. Remember the Ki is, for diazepam is 10. Adding a hydroxyl group gives you a Ki of 25. So larger groups give you higher Ki, which means less affinity. So what if you add in even larger groups? Let's say you add a CH3 group. It's even larger. Ki for that would be 50. Oh, here's a cloud. Don't memorize these structures. The cloud. What's that movie where he's like, it's in the cloud? I don't know. Anyways, so larger groups give you higher Ki's, which means decreased affinity. Now, what if you have a a carboxylic acid attached, which gives you principle number 1. Number 2, COOH gives you no binding. Way too big. But chlorazepate, which is the structure I just showed, but don't memorize it, it's in the cloud. Brand name? Oh, quiz, what's the brand name for chlorazepate? Transine. I don't know how you pronounce it, whatever. Transine. Chlorazepate is a prodrug. So that's why chlorazepate works. So even though chlorazepate has this C double carboxylic acid, which means it shouldn't bind, it actually is a prodrug, which is why it works. TPS, it's a prodrug for norazepam. So position 3, summary. Hydrogen's optimal, but adding larger groups gives you higher affinity or lower affinity or a higher Ki. Principle number 2, adding a carboxylic acid doesn't allow the molecule to bind, but chlordiazepate, which has a carboxylic acid, binds or actually works as an anxiolytic because it is a prodrug for diazepam. Okay, so position 4 requires an electronic requirement, meaning it needs electrons. Nitrogen 4, which is nitrogen 1, 2, 3, 4. Nitrogen 4 is optimal because it has this double bond right here. But you can replace it with an sp2 hybridized carbon, meaning you can replace it with a C-double-bond-C, C-double-bond-S, or a C-double-bond-N. To explain this, so in the receptors, there's 3 different binding sites. There is an aromatic binding site, an electronic binding site, or an electron needing binding site. So here are your electrons right here. Double bonds are electron rich. So this electronic binding site needs electrons, and there's two electronic binding sites. There's that one and that one. And then auxiliary binding site. So this molecule, which is actually diazepam, not in the cloud because you actually have to know diazepam. Diazepam fulfills the electronic binding site requirements because it has electron-rich double bond here and an electron-rich double bond right here, which fulfills the electronic binding sites. Now, which illustrates the concept that N4 is optimal. Nitrogen 4 is optimal. But what if you replace it with an sp2 hybridized carbon, like in clobazam? This one, what is happening? This one will be in the cloud, because you don't have to memorize the structure, know the concept. I'm just going to clobazam. Okay, so this is clobazam. If you see, you replaced in position 4, 1, 2, 3, 4. This position 4. You replaced it from a nitrogen to an sp2 hybridized carbon because you have a carbon-carbon double bond. And you still fulfill the electronic requirement because you bind at the 2 electronic binding sites. Number 1 over here because you have the electron-rich double bond with oxygen, and over here because you still have the electron-rich double bond oxygen. So, illustrating the principle that position 4 requires an electronic requirement, and nitrogen at the 4th position is optimal, shown here, but you can still replace it with an sp2 hybridized carbon over here, and you still get activity. Okay, so position 5. There's 3 principles. So compared to diazepam, I'll explain everything. Don't worry. Principle number 1. Compared to diazepam, 2-X-phenyl has a higher affinity or lower Ki. So if X equals F, fluorine chloride or trifluorocarbon, so CF3. So illustrating principle 1. Principle 1. If you substitute, so this is your let's see. This is 2X right here. So remember, X would equal fluorine, or CF3. So that's your 2' position. So if, oh, this is awkward. That's wrong. Hold up. Okay, so this is actually your 2' position I'm talking about. So X here would equal FCl CF3, my bad. So let's see. If you have a fluorine here, or a Cl, or a CF3, at this attachment right here, you will have, like I said up here, higher affinity and lower Ki than diazepam. So 2-X-phenyl, higher affinity, lower Ki. So add a fluorine, chlorine, or a CF3 at this 2 position on this phenyl ring on the bottom, and you get higher affinity or lower Ki than diazepam. It's in the cloud, so don't know the structure, but know the concept. Number 2. Number 2, a 2-pyridyl has a lower affinity or a higher Ki than diazepam. So this is your pyridyl group, just a 6-ringed structure with 1 nitrogen. So pyridyl group is 6-ring structure with 1 nitrogen. So if you replace the phenyl group with a pyridyl group, you get lower affinity or a higher Ki than diazepam. Okay, principle number 3. If you substitute your phenyl ring, your phenyl ring at the bottom, with a C double bond O, you get higher affinity or a lower Ki. So there is no phenyl group here. We just replace it with a C double bond O. And this has a higher affinity or lower Ki than diazepam. So to get different affinities and different Ki's, number 1, you can change the 2' position on this phenyl group to fluorine, chlorine, or CF3. You get higher affinity, lower Ki. Or you can replace the ring at the bottom with a pyridyl ring, and you get a lower affinity or higher Ki. Or just remove the ring altogether and replace it with a C double bond O, and you get higher affinity or a lower Ki. Okay, so position 7. Okay, so electron withdrawing groups enhance affinity or increase affinity or lower Ki. So this is position 7 right here. The order of affinity, so order of affinity goes NO2 has more affinity than NO2 has more affinity than CF3, which has more affinity than Br, which has more affinity than Cl, which has more affinity than H. Or if you want to write it in terms of Ki, which one do you think would go first? Which one has the largest Ki? H, because it has the lowest affinity. So H has a lower affinity. H has a larger Ki because of the lower affinity than Cl. Which has a higher Ki than Br, which has a higher Ki than CF3, which has a higher Ki than NO2. If you want to memorize it, you can go knockoff Burkles. Like Burkles the brand. This dude buys knockoff Burkles because he's too cheap to buy the real brand. Burkles. So, where'd I get that? Knockoff Burkle. And there's a silent H. Knockoff Burkles. Knockoff Burkles are knockoffs of the brand Burkles. Knockoff Burkles. Knockoff Burkles because the dude's too cheap to buy real Burkles. I don't know what Burkles are, I just made it up. If you have, illustrate the concept. If you have an NO2 here, that has a higher affinity or a lower Ki than if you substituted it with, ooh, wow, that's awkward, CF3. And CF3 has a higher affinity or lower Ki than BR. Whoa. BR. BR has a higher affinity or lower Ki than H, hydrogen. This is going in the cloud, because please don't memorize this, just to illustrate examples. So yeah, electron withdrawing groups enhance affinity or lower the Ki. Here's your order of affinity, and here's your order of Ki. It's basically the reverse of affinity. If you know the affinity, knock off Berkels. You know the Ki, just the reverse. Okay, so other substitutions, for example, substitutions at 6 position, 8 position, 9 position give you decreased affinity or higher Ki. And also substitutions at 3' and 6', so on the phenyl ring, give you inactive compounds. Okay, so after talking about the simple benzodiazepines, now we have the anylated or the fused benzodiazepines. The first one we're going to talk about are the triazobenzodiazepines or the TBZs, and these are generally more potent and shorter acting than your simple BZs. More potent because they have higher affinity, and shorter acting because they have few active metabolites. Shorter, few active metabolites. So your prototype is alprazolam. This is alprazolam, not in a cloud because you have to know it. So the Sapphire includes 2 principles. Number 1, it's optimal to have a 1-methyl, this methyl, this is the 1 position, 1-methyl, or you can have it as a hydrogen. So instead of having a methyl, you can just have it as a hydrogen. Number 2, and nitrogen 3. 1, 2, 3. And 3, which is this one, can be replaced by an sp2 hybridized carbon. Remember, your sp2 hybridized carbons are your carbon double bond oxygen, carbon double bond nitrogen, or carbon double bond carbon, nitrogen, oxygen. Okay, so carbon double bond oxygen, carbon double bond nitrogen, or carbon double bond carbon. Said that right. Okay. And if you do that, you would make it an IBZ, or an imidazobenzodiazepine. To illustrate this, I'm just going to redraw the top ring, so NCH3. You have a carbon double bond carbon. Now, carbon double bond oxygen, whatever. You have 2 nitrogens, so it makes an imidazobenzodiazepine. So your triazobenzos have 3 nitrogens. Azo means nitrogen, so tri means 3, azo means nitrogen. So triazo means you have 1, 2, 3 azos or triazo benzodiazepine. Your imidazobenzodiazepine does not have 3 azos or triazos. It has 2 azos or 2 nitrogens. So your IBZs have 2 nitrogens. Your TBZs have 3 nitrogens at the top ring. Look at the top ring. Yep. Now here's your metabolism. Okay, so your metabolism. First step in metabolism is alpha hydroxylation of the 1-methyl group. So what that means is, here's your 1-methyl group. You're going to hydroxylate it to form the methyl group plus a hydroxyl. Now the minor root, you're going to oxidize it to, you're adding one more oxygen to make it a carboxylic acid, and you're removing the carboxylic acid, and you're just leaving a straight triazobenzyl group. Triazo ring. Now the major pathway is, first step, alpha hydroxylation. So you're going to add a hydroxyl group to the 1-methyl group. Then you're going to glucuronidate this. Simple. So basically, minor route, both routes you're adding hydroxyl, but minor route you're taking the hydroxyl off. Major route, you're going to keep the hydroxyl on but glucuronidate it. Easy. So your benzodiazepines, your IBZs. Remember, I said your IBZs have 2 nitrogens, your TBZs have 3 nitrogens. So here's your 2 nitrogens at the top ring. It's in the cloud because I don't want you to memorize this. It's just to illustrate that IBZs have 2 nitrogens because TBZs, triazos, have 3 azos or 3 nitrogens. TBZs, IBZs have 2 nitrogens at the top. 1, 2. Okay, so finally in this benzodiazepine part, we're going to talk about the benzodiazepine related agents. So these bind to the benzodiazepine receptors but do not have a benzodiazepine ring. These include your imidazopyridines like zolpidem or zolpidem, and your pyridoindoles or your beta-carbolines, which includes beta-CCM. So first off, we're going to talk about your imidazopyridines, which includes zolpidem. He talked about the concept of chiral switch, which means you produce the molecule with either R isomers or S isomers, but not with those containing both R isomers and S isomers. So, for example, cetirizine, Zyrtec, I think is the brand name, has an R and an S isomers in it. But levocetirizine, which has just one of those isomers, Xyzal, is an example of chiral switch because you only have one isomer instead of the R and the S isomer. In this example, he has isopicolone or Lunesta, which has the S, because S-zopicolone is the S isomer instead of the RAS, the S and the R isomer in zopicolone. So imidazopyridines, think chiral switch, also think zolpidem. Next off, pyridoindoles or beta-carbolines. So the beta-carboline ring itself does not bind to the BZ receptor. I'm not drawing it because you don't have to know it, but the beta-carboline itself does not bind to the BZ receptor, but the ester inside the whole structure does. So the beta-carboline itself does not bind to the receptor, but the ester within the structure does. Hopefully that makes sense. If not, let me know. Okay, now the mechanism of action of benzos. I think the pharmacology lecture really does a really good job, so refer to that. She's a really good teacher. If you do have any questions though, let me know, or let the teacher know, or let Glenn know if you're really ballsy. But here are some key terms that probably aren't in that pharmacology lecture that he probably wants you to know. Number 1, GABA binds at the orthosteric site. Remember that. GABA binds at the orthosteric site. Remember that benzodiazepines bind at the allosteric site. Technically, they act as positive allosteric modulators. That's a technical term for it. Meaning they positively or synergistically or they enhance the effect of GABA. Synergism or enhance. However, remember that they have no effect on their own. Benzodiazepine antagonists are also known as silent antagonists. They block the effect of benzodiazepines at the allosteric site. They do not bind to the orthosteric site. They bind to the allosteric site. Think flumazenil. That's your benzodiazepine antagonist. They do it competitively. It's competitive inhibition, but as I said, they do not bind to the orthosteric site, so they don't affect GABA. Finally, you have your negative allosteric inhibitors. So if positive allosteric inhibitors enhance the effect of GABA, negative allosteric inhibitors diminish the effect of GABA, aka they close the ion channel. Which ion channel? The chloride ion channel. Ugh, pop quiz. Okay, so Glennon had this table. He actually wrote this table. Fun fact. Yeah, here's this table he wrote with his wife, Dr. Ducat. So here's the table they wrote. He said pay attention to those related to CNS disorders, which I wrote at the bottom. Also pay attention because your 5-HT3 family is the only ion channel superfamily. The rest are GPCRs. Remember that. He even did it in bold for you over there. If you don't see it, it's right here. Right here. It's in bold. Remember, 5-HT3 is your only ion channel superfamily. Other than that, I don't know. Memorize those related to CNS disorders, TBH. I don't even know how I'm going to memorize this. But the table is there. Not really concepts to explain. Looks pretty self-explanatory. But special thing, if you didn't notice in the slides, he wants us to know these following structures. Okay, so here are the structures he wants us to know that are related to the table that he made. If you don't believe me, check the slides. It says structure equals HO dash number. Just in case. So these either relate to the table or somewhere in the lecture. Flumazenil, I remember that because flu means fluorine. Here's your fluorine. This is beta CCM. Remember earlier I talked about beta CCM having an ester group? Well, here's the ester group. This is actually beta CCM. This is the ester group. So beta CCM, look for the ester group. Flumazenil, look for the fluorine. Sumatriptan. S is for sulfur. Here's your sulfur. Ketanserin. Oh yeah, sumatriptan is in the table. Beta CCM and flumazenil don't look like they're in the table, but they are definitely in the lecture, and I just talked about them. Flumazenil is your benzodiazepine antagonist. Beta CCM is your benzodiazepine related agent. However, the last three are definitely in the table if I couldn't find those last two earlier. These last three are in the table. Sumatriptan is belongs in the family 5-HT1. S is for sulfur. Ketanserin. While this also has a fluorine, look for this little wiggly thing. Looks like a bird. Look for the bird. Yeah, look for the little bird over here in the middle. That's ketanserin. Bird with the fluorine is ketanserin. Ketanserin is somewhere in this table in the 5-HT2 family, specifically a selective antagonist. And finally, Zofran, aldanthotron. That belongs in the 5-HT3 family. That's in the table too. So these last three are definitely in the table. Sumatriptan, ketanserin, aldanthotron. The first two, beta CCM and flumazenil, may or may not be in the table, but they're definitely in the lecture. We just talked about them. Sumatriptan, look for the S. Ketanserin, look for the bird. And the F. Looks like a bird, right? And then here's the F, the fluorine. Ondansetron, TBH. To me, ondansetron sounds like a robot's name. You know, here's the eye of the robot. No, look, here's a little neck. Here's his body, and here's his little arms. Yeah, Danzatron to me sounds like a robot. So when in doubt, you got the robot over here for the Danzatron. Catanserin, look for the little birdie with the fluorine. Sumatriptan, look for the S. Sulfur. Beta CCM. Okay, it might look like a robot, but you definitely know beta CCM has the ester. And this ain't no ester with a Danzatron, I can tell you that. Flumazanil, you got your fluorine for flumazanil. Finally, the last part of the presentation, his lecture, serotonergic agents. There are two types. The aminotetralins, which includes 8-hydroxy-DPAT, which is a 5-HT1A agonist. And then your second agents are your arylpiperazines. These bind to the 5-HT1A receptor also. Your simple arylpiperazines have modest affinity and little selectivity for the 5-HT1A receptor, but your long-chain arylpiperazines, or your L-caps, have higher affinity and enhanced selectivity for the 5-HT1A receptor. Your general structure of your L-caps are your aryl ring, your little birdie with 2 nitrogens, your spacer, and your terminus. So in buspirone, buspirone is important, not going into clouds, going in a box because it's your prototype. So buspirone or buspar is your prototype for your L-caps. So here's your aryl ring. Here's your birdie with 2 nitrogens, so your spacer, and your terminus. I lined everything up with a general structure so you can see everything. So your aryl ring, your birdie, your spacer, and your terminus. Hopefully that lines up. It is a pop quiz, mechanism of action, go. It is a partial 5-HT1A receptor agonist. Okay, so here's your SAR for your L-caps. 3 parts. Let's show you L-cap while I'm there. Okay, so 3 parts. Your aryl ring, your spacer, and your terminus. So your aryl ring, optimizing the aryl ring involves putting a phenyl ring. You know what a phenyl ring is. Substituted phenyl. So here's your phenyl. What is wrong? Substituted phenyl with your with a substitution on it. For example, a chlorine, or a heteroaryl, which is what buspar is. Which means a heteroaryl means anything, a ring with anything but a carbon. So buspar has 2 nitrogens, so it's a heteroaryl. A spacer is 2 to 5 atoms, branched or unbranched. So here's your 1, 2, 3, 4. That's 4 atoms. Falls in 2 to 5 within the 2 to 5 atom limit. And that's 2 to 5 atoms, can be branched or unbranched. For example, you could have a branch, you add a carbon here, some more carbons, add some more branches. Those are your branches. Those are just basically more carbons. I'm going to erase that because that's definitely not in buspirone. I'm just adding for examples. So buspirone fits the SAR because it has 4 atoms. It fits within the 2 to 5 atom branch. So 1, 2, 3, 4. Finally, the terminus. To optimize it, you can put an amide, an imide, or an aromatic ring, and it has to be wide. So this is pretty wide. So I don't know what happened to the audio here, but I just wanted to highlight that non-190, not the Indian bread, but the chemical, is the first 5-HT1A receptor antagonist, and it also functions as an alpha-2 adrenoceptor antagonist. Okay, to review, remember to name benzos, divide them into their components, number them from nitrogen to nitrogen, and letter them following that same numbering scheme. Lowest number and lowest letter preferred. Actually required, not even preferred, required. Your simple benzos, your prototype is your diazepam. Here is your metabolism, wrote it out in word form and in chemical form. Remember, 9 plus 4 is 13. What's your minor root? 13 is bad luck. Never go the minor route because it's bad luck. Let's see. Ooh, quiz question. So, why is oxazepam a short-acting benzo? Because it has no active metabolites, and it's the last chemical in the metabolism scheme. So, if you can skip all these steps to get the oxazepam, then you get a really short-acting drug. Also, there are no active metabolites, so you don't get any long-lasting effects. So why is diazepam a long-acting benzo? Because you get all these active metabolites, including oxazepam. So oxazepam is short-acting because it has new active metabolites, and diazepam is long-acting because it has all these active metabolites. Cool. Ooh. Another quiz question. Why is chlorazepate... Never mind. I'll ask that later. Awkward. Anyways, blah 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 metabolism. Remember the difference between SAR and Sapphire? Actually, let me review the metabolism better. Blah blah blah. Remember, when in doubt, demethylate it out. So clorazepam to the major pathway, demethylate it, convert it to C double bond O, get demoxepam, which is norazepam N-oxide. You lose the N-oxide to N, you get norazepam. Hydroxylate it at the 3 position to get oxazepam, glucuronidate it, and excrete it. Minor pathway, demethylate it, when in doubt, demethylate it out. Then you convert it to C double bond O to get demoxepam, which is norazepam N-oxide. Add a 9-hydroxy or 4' hydroxyl. Remember, 9 plus 4 is 13, bad luck. Minor roots, bad luck. You get an aromatic group, you glucuronidate it, and you excrete it. For diazepam, when in doubt, demethylate it out. Demethylate it to get norazepam. Hydroxylate it at the 3 position to get oxazepam, and you glucuronidate it. Minor pathway, diazepam, you hydroxylate it at the 3 position to get temazepam, demethylate it to oxazepam, and glucuronidate it, and excrete it. So basically the minor pathway is the opposite of the major pathway. So now we're talking about review your simple benzodiazepines. Remember, higher Ki means less binding, or less affinity. So position 1, N is optimal but not required. You can replace the nitrogen with an sp2 hybridized carbon. Remember, sp2 hybridized carbons are carbon double bond nitrogen. Carbon double bond sulfur, carbon double bond carbon. Basically, carbon double bond anything. Pretty much anything. In this lecture is sp2 hybridized carbon. Bigger groups attached. Number 3, bigger groups attached to the nitrogen lead to lower affinity or higher Ki values. Position 2. sp2 hybridized carbons are preferred or optimal. Position 3. Hydrogen is optimal with larger groups leading to less affinity. So the larger the group at position 3, the less affinity you have, exhibited by the carboxylic acid, which has no binding. However, chlorazepate, brand name Transine, works as a benzo. Why? Because it's a prodrug for norazepam. Okay, here's the pop quiz. Pop quiz. Why does chlorazepate have a longer onset time than most of the benzos? Because it's a prodrug. So you got to convert it to norazepam first for it to work. and that takes time, a lot more time than oxazepam, for example, when you're just the last step in the metabolism process. So the farther you are in the metabolism process, the more longer onset time you need. That's why you have to understand the metabolism, because if you understand metabolism, you understand why things have longer onset times, why things have longer durations. So yes, chlordiazepine has a longer onset time because it's a prodrug. Position 4. The electronic requirement. Remember, you need double bonds. Remember, double bonds are electron rich, and you need double bonds in the electronic binding sites. So, nitrogen is 4 is optimal, but we can replace it with an sp2 hybridized carbon. Basically meaning an S carbon double bond into pretty much anything. But to be safe, list the ones I listed here. Position 5. 2-X-phenyl has higher affinity, lower Ki. 2-pyridyl has lower affinity, higher Ki. Carbon double bond oxygen has higher affinity, lower Ki. Remember, your X is fluorine, chlorine, or CF3. Stop. Position 7. Electron withdrawing groups. Remember, knock off Berkels is your affinity. Your Ki is your opposite of that. So Na has your highest affinity, followed by Kuf, followed by Ber, followed by Kol. Knock off Berkel. Let's see. Electron withdrawing groups enhance affinity. Substitutions at the 6, 8, and 9 positions decrease affinity or increase your Ki. Push 3' and 6' substitutions make the drug inactive. Finally, your anylated or fused benzos. Triazobenzenes have 3 azos, so 3 nitrogens. These are generally more potent and shorter acting than simple benzos. Your prototypes are prazolam. Remember your sapphire. The 1-methyl is optimal. Oral hydrogen is optimal. And the third, nitrogen 3 can be replaced by sp2 hybridized carbon. Basically a carbon double bonded to pretty much anything. And if you do make it an sp2 hybridized carbon, you make it an imidazobenzodiazepine. Why? Because remember, imidazobenzodiazepines have 2 nitrogens, triazos have 3 nitrogens. Here's your metabolism route for your TBZs. Remember, your first step is alpha hydroxylation. Your minor route is when you remove the CO2. Oh, I'm so sorry. Remove the CO2. Major route is when you keep the hydroxyl and eugleucoronidated. Showed you your IBZs. Your benzodiazepine related agents are your benzodiazepines like zolpidem. Remember your chiral switch when you include only one isomer instead of both isomers. And you also have your pyridoindols or your beta-carbolines. Both these sets of drugs bind at benzodiazepine receptors, but they do not have the benzodiazepine ring. Your beta-carbolines itself does not bind to the BZ receptor, but the ester in the structure does. Mechanism of action. Review the pharmacology lecture. She does a really good job. But also know your positive allosteric modulators. Ooh, that's a positive allosteric modulators. Oh, crap. Oh yeah, okay. Your positive allosteric modulators enhance the effect of GABA, but do not affect GABA itself because they don't bind to the orthosteric site. BZ antagonists do not bind to the orthosteric site, but they competitively compete with benzodiazepines at the allosteric site. For example, flumazenil. Negative allosteric modulators close the ion channel by binding to the allosteric site and diminishing the effect of GABA. Know the table that Glennon and his wife made. So cute. Pay attention to these CNS disorders discussed in the table. Know these structures. Flumazenil has your fluorine. If you don't believe me, look at the slides. He definitely says H. O. Structure HO dash number. Flumazenol has the fluorine. Beta CCM has the ester. Sumatriptan, look for the S. Ketanserin, look for the birdie with the fluorine. Ondansetron always sounds like a robot to me. Here's a robot's neck and his body. Here's his arms. Finally, your serotonergic agents. You have your aminotetralenes, which includes 8-hydroxy-D-PAT, which is a 5-HT1A agonist, and your arylpiperazine, which is also a 5-HT1A binder. You have your simple ones, which have modest affinity and little selectivity, and your long-chain ones, which have higher affinity and enhanced selectivity. Your general structure is included here. You got your arrow ring, your your arrow ring. Oh crap! Your arrow ring, your 2-nitrogen ring, your spacer, and your terminus. SAR for that, you have to have, for the arrow ring, a phenyl, substituted phenyl, which is a phenyl with a group attached to it, or a heteroaryl, which is what boost bar is because it has 2 nitrogens instead of just straight carbons. Spacer has to be 2 to 5 atoms. Boost buron is 4 atoms. Terminus can be an amide, imide, or an aromatic ring / a phenyl ring. It has to be pretty wide. Alterations can affect binding at the 5-HT2A1 receptor, D2 receptors, or the alpha-2 adrenoceptors. Finally, non-190, not the Indian bread, is your first 5-HT1A receptor antagonist, and also a alpha-2 adrenoceptor agonist. Okay, finally, thanks for watching the video. If you have any comments, feedback, I always appreciate feedback. Anything good, anything constructive, feel free to leave it at polev.com/CHRISTIANRUI629. You can also find this in the YouTube video description found below. I made video descriptions, pretty cool. Just click on the link below and yeah, you can also download the videos now. You can also still download the videos, just follow the link below in the YouTube description. Thanks for watching, good luck on the test.